Okay, so now we're going to look at transformers. Everybody knows what transformers are, but the ones that we're going to see are even more exciting than this one, which are transformer networks. And we're going to start by looking at the attention mechanism, which is at the basis of transformers, and then see the motivation and why we use transformers and how the transformer network looks like. And most of this lecture will be explaining the implementation of a transformer model and how you can experiment this to translate Portuguese to English. So this is a demo that you have on your carriage documentation. I'm going to explain a bit the code because it's not explained on the demo. There are lots of details about using carriage that are outside the scope of the course. So you don't need to know this for any grading, the details here. But I thought it was a good idea to show you a bit deeper what we can do with carriage, the TensorFlow, and show you something that is a bit more realistic than the examples that we've been using so far. Okay, so let's start with the idea of the attention mechanism. The inspiration here is on the way our brain works, or in general in animals works, which is that we don't pay equal attention to all the inputs that we get. So we have some selection mechanism that gives more attention to what is relevant and less attention to what is not. And the motivation for this was to try to mitigate the problem with recurrent networks that we saw previously in trying to learn long-term dependencies over long signals or long inputs. So imagine that we are creating a translation system between English and Chinese, for example, where we have a recurrent network that takes a sequence of words and creates a vector of fixed length that describes this context, basically, this sentence. And now we feed that as the starting point of another recurrent network that will generate the words in Chinese and try to produce the translation for the English sentence. But the problem here is that this encoder network will be likely to start losing some relations between long distance elements in this sequence, and then maybe this context will not be, this vector will not be very good to represent the sentence and so on. So we saw several ways of trying to fix this with skip connections and things like that, but the attention mechanism was proposed here in this context to try to create a dynamic context for the decoder. So basically imagine that we have this architecture here. So this one is from 2014, where we have a bidirectional recurrent network for the encoder. Remember that this one makes states depend on the following state, and in the other direction depend on the previous state. But basically it's a recurrent network that takes in the original sentence. And then we have here a transformation that is basically a linear transformation of this that is added to the output of this network. But this is a learned linear combination that can then give a context vector that focuses more attention on more relevant elements here. And also this can then be done dynamically during the decoding and so on. So this actually improved a lot the performance of this kind of translation networks, because it allowed the network to learn what to look for in the patterns on the encoder. But actually this worked so well that in 2017 there was this proposal of a transformer network that uses the attention mechanism but does away with the recurrent network. It's just a feed-forward network, so it's much easier to train because we can parallelize everything. We don't need to wait for the different type of steps. It has fewer problems with convergence and so on. And now we have a feed-forward network that can take an input sequence, for example, sentences in one language, take the previously generated tokens, and predict what the next sentence will be. So if we want to use it to generate a new sentence, we just pass through several times on the network, and it will output the next word each time. This used the scaled dot product attention. So imagine that we have this set of values and we want to figure out which ones to pay closer attention to. So we're going to use a softmax on a vector, and this softmax will give us values between 0 and 1, all adding up to 1, and we're going to multiply that by the values vector, so that we have more attention to some that have a higher value on the softmax, others that have a lower. And what we input into the softmax is this product, the inner product of two other vectors, which they call the query and the keys, but this is just conceptually, it can be anything. It can even be the same vector for self-attention, for example. Scaled here by the depth, so imagine that this, in the particular problem that we are using, these are actually matrices, because we are representing a set of words as a matrix where each word is a vector. Each word is represented by a vector. A sentence is a series of vectors, so it's a matrix here. And this depth is the size of the representation of each word. But basically we take two of these, we multiply them together and rescale. We use that for the softmax, and this tells us which parts of the values matrix we must pay more attention to or less attention to. So this is part of the transformer network. We can represent this like this. So basically multiply these two using the scale, then the softmax, and multiplying by the values. There is an additional step here where we can mask part of the input, because suppose that we are representing sentences that can have up to 100 words. But most sentences have far fewer than 100 words. So we may want to mask all the part that is irrelevant, so that the network is ignoring that. Or suppose that we are training the network, so we have a sentence in one language, a sentence in another, but we only want the network to look at the first words of the second sentence in order to predict the next word. In that case, we need to mask the following word so that the network does not just copy what we have there. So there is also this mask for training and using the transformer network, but this is the general mechanism of the attention here. And actually it's created in this multi-head attention, where we take linear combinations of these, the values, the keys, and the queries, and we split these into parallel attention heads, and then concatenate everything at the end and take a linear combination of that concatenation. These linear combinations are just to keep the correct size here, and what we are doing is several of these attention mechanisms in parallel. This allows the attention mechanisms, some to focus on longer range patterns, other to focus on the shorter range patterns, and so on. So this improves the performance here. And this is the architecture. Did I say? No, it's okay. This is the architecture of the transformer network. We start with the input. The input is a vector of integers where each integer represents a word. Then we have an embedding layer. This is basically, you can imagine this as a table or a matrix where each integer is converted into a vector that represents the word. Now this embedding layer that does this conversion is also trained along with the transformer in order to create the best representations of the words for whatever is going to happen here in the translation. Then there is this positional encoding, because the same word appearing in different places on the sentence can have different roles in the sentence. So we add this positional encoding that to the vector for the word, so that the vector of the word is slightly different depending on the position it appears on the sentence. I'm going to go into a bit more detail about this, but then the input, this would be, for example, Portuguese sentence, the words get embedded, so a sequence of integers with the indexes of the words. Now we have a matrix of vectors, each vector for each word, and a matrix for the sentence. This gets added the values for the positions of the words, and then we go into this encoder, which has a sequence of n layers like this. The first layer is a multi-head attention layer that is receiving the same input 3 times. So basically this is self-attention. The query, the keys and the values are all the same input here. Then we have this residual connection here, because now we're adding the input to the output of the multi-head attention. And then we have this special position-wise or point-wise feed-forward network that I'm going to talk about, but that is going to go through all of the words in the sentence and another residual connection. And the output of this will, all these layers will go into the decoder. So the encoder can have n of these, and then the output goes into the decoder. Basically, this is creating a representation of the sentence on the original language. And now, what we have here is we input the sentence created so far. For example, we can just input the starting token and mask everything else. And what we get there on the output is a softmax with the probabilities of what the next word will be. So suppose that we have 10,000 possible words. This would be a softmax with 10,000 different probabilities, each one indicating the probability of each word, so we can select the best one, the one with the highest probability. This would be the next word. Now we put that again here, and we obtain the third word, and so forth. So what this decoder has is, again, this multi-head attention for the input here. This one will be masked because we need to hide the following words. We only want the network to receive the previous words, not to look at the future. Then again, these keep connections and the same kind of network here. And then we can have n layers like this. But what they also receive, so this first attention block is a self-attention one because it's only looking at the input. But this one here is receiving the output of the encoder. So this attention block will focus on different parts of the sentence created so far, depending on what the original sentence is. And now we can create multiple blocks like this, and then we have the softmax at the end. So this is the architecture. Now let's see, this is the tougher part of the lecture, how we can implement this. So if you want to look at the whole code and follow it there, you have the tutorial on the Keras documentation. There is no big explanation there, so that's what I'm going to try to do here. There are lots of sophisticated tricks here, especially working with the tensors. So there are things that we may need to do in different parts, but if we create the right tensor, the TensorFlow can do it all at once. That is a bit confusing, but it's a lot more efficient. So about these things, don't worry too much. I'll explain them briefly, and then you can try the code. But those fall a bit outside the scope of the course. But this is just for you to have something that actually works, and I think that's cool. You need to install the datasets and the text part of TensorFlow because you need the tokenizers and the datasets for the translation. But you can do this as long as you do it on the environment that you have TensorFlow installed. So this would be just to download the data and the tokenizers for Portuguese and English. Tokenizers are just these models that basically have a dictionary of the words. They identify the words and then they create an integer representing each word. There may be some more sophisticated processing here because words have variants, for example, different conjugations of the same verb or things like that, or plural and singular and so on. So the tokenizer can process all of those things. And basically, if you give it a sentence, it will give you a vector of numbers identifying all the words and including the special token for the beginning and the end and so So this is, you get the data for the translation of Portuguese to English. These are a series of examples of sentences translated from Portuguese to English. Then you download these converted, this tokenizer for the Portuguese to English translation, and basically this is the one that will convert strings into vectors of integers with the index of each word there. So this would be our tokenizers here that we load from this model. These utilities that you can use to get the files and the data, they keep everything in cache. So this could be the same folder where you're working on. So if you don't have the models there, it downloads them, but if you have them, it just doesn't do anything, and you can just load them again. Okay, so this only needs to download it once if you leave it on the folder. Now we're going to create this function to tokenize the sentences. Basically, we have a sentence in Portuguese and English. We're going to tokenize and convert to tensors, and now we have two tensors, which would be tensors of integers, where we have the indexes of the words in each sentence, one in Portuguese, one in English. And this is something that we did not see before, but this can be useful for, in general, dealing with large data sets, because this is the data set class on TensorFlow that you can use to manage loading data from the disk. So if you can put everything in memory, it's not a problem. If you have something that is a bit larger, you need to schedule how it's read and how it's buffered in memory, randomized, and so on. So basically, these data set objects, which are the ones that you have here, so these train examples and val examples are data sets. You can use this kind of pipeline processing where you can keep elements in cache. You can specify the size, the number of examples that will be shuffled. So in this case, it will shuffle 20,000 at the same time, because it needs to put them in memory to shuffle them. So you may not be shuffling everything at once, but at least you're not overloading your memory with the data. This is the size of the batch, 64 at each time. Then you can use mapping. So basically, this is the mapper that converts the data that you're reading into the data that you need for the network. There is this auto-tune on the parallel calls allows TensorFlow to optimize the use of different threads. So if you have something training on the GPU, it can be using the CPU to convert your data at the same time, and so on. So this allows for more sophisticated and more efficient processing of the data. And the same thing for prefetch. So it can be fetching the data while it's still not needed, but while it's waiting for something to process on GPU, it's already reading the disk to get the next set of batches or something like that. So this auto-tune basically lets TensorFlow figure out what is the best way of doing this. And now we have the train and validation batches, which will be these data set objects that we are creating from the train examples and the valid examples. So basically, we take these data set objects and we use all of these functions, not functions, but okay, I forgot the name, but all the functions in the objects to create this pipeline and then obtain the object that can give the batches for the training and the validation. Now, what we also need to do is to add to the vector for each word some modification that encodes the position. This is one way of doing this. We use, let's assume that we have a maximum of, say, 10,000 positions or 100 or something like this. This would be the depth of the model. This is the size of the vector that represents each word. And now we can put on the even numbered indexes on this vector that represents each word this sign value that depends on the position of the word on the sentence. and for the odd number we use cosine. So this is something that is a bit weird, but when you look at the graph, so basically here the color represents the value you get from these functions, and this is the depth of the representation. So let's say we are representing each word with a vector of 512 elements, and this is the position on the sentence. So as you can see, positions that are similar have very similar values here, but as we go to different positions, more and more distance, we start having a greater variance on the same positions on the encoding of the word, because all of these are shifting to a different place. So if you look at position 100, for example, here it has a high value, here it has a low value, here it has a high value, and so on. And these have all different combinations here. So when we add these vectors to the representation of the word, we are creating a slight difference that depends on the position along the sentence. And this is enough to inform the network that this word is not the same, is not in the same position as it was in a different example. So this is basically doing this. This assumes 10,000 maximum positions here. This is the depth of the model. So in this case, I think it's 128, if I recall correctly. And then we create the angles, and then we use the sine and the cosine, the sine for the even numbered indexes, the cosine for the odd numbered indexes, and then we typecast this into a tensor. So basically, we are applying this formula here to create the positional encoding for each position of the sentences on our data. We also need masks, so this padding mask basically creates a vector of zeros and ones with a 1 on all the positions where the sequence is 0. So if you have an input of a sentence where you have the indexes of all the words, then you have lots of zeros where you don't have words, because not all sentences have the maximum length. So this basically creates a mask that indicates these first are words because they have zeros on the mask, and the other ones are not words, they have ones on the mask. This other, the look ahead mask, is actually this matrix which has masks that keep unmasked the first token, or the first 2 tokens, or the first 3 tokens, and so on, which are necessary when we are training the transformer, and we need to feed into the transformer the original sentence, the translated sentence, but we don't want the transformer to look ahead on the translated sentence to see what the next word should be. We want the transformer to tell us what the next word should be. So basically, to do that kind of teacher forcing, where we are giving the transformer the previous words correctly, we need this mask to hide the next word. So basically, this one uses this from the linear algebra model, this band part that takes the diagonal here of the matrix, and in this case, this upper corner, and returns that as the mask. So another thing that we need to do for the attention module is this scale dot product, which is basically multiplying the query and keys matrices by transposing the keys matrix so that we have a matrix of the same shape, and then we are going to scale this by the square root of the depth. So this is basically the size of the representation we are using for each word. And if there is a mask here, we are going to add to these logits. So this would be the input to the softmax. We're going to add to that minus 1 billion wherever the mask has a 1. So basically this gives a very negative value to the logits in those positions, which means that when we apply softmax, all those will be set at 0, and the true distribution will be on the part that is not masked. Okay, so this is how the mask is used in this case. Now we multiply this softmax here by the values, and we have the attention applied to the values. So basically, we use the query and the keys to get the input into the softmax. After applying mask, we have some values that are higher and others lower, and we apply that to the values tensor tag. This output attention weights is, if you use the tutorial, you can also then look at the values of the attention weight as it is learning how it is shaping these, for each example, how the attention weights change. Okay, so now we have the dot product attention. We can create the multi-head attention, and this would be an example of creating a cabbage layer. You can use that to add your own types of layers to the network. So basically, we are creating a multi-head attention class that descends from the layer basic class on cabbage. On the initializer, we call the initialization of the parent here, and then we define the number of heads that we have here and the depth of the model. So this is the size of the representation we have for each word in our broader model. But now, if you're going to break that down into different heads, we need the depth of the model to be a multiple of the number of heads here. So if it's not, this will not work because we cannot split it into those heads. So this is this assertion here to make sure that that's okay. And now the depth for each head will be the depth of the model divided by the number of heads, and we now create these dense layers, these dense linear layers for the different heads. So this is for the different inputs: the query, the key, and the value. Basically, these are these parts here. Okay, so we have these linear combinations of the inputs. We use that with the dense layer without an activation function, and that will then go be split and go into the multi-head attention. Okay, so now to split, we just reshape. So this is a trick. Imagine that you are doing this in parts. We would split into those number of heads, and then we would compute for each of the heads and then concatenate at the end. But this is a bit more confusing but a lot more efficient, where we are just reshaping the input here, taking into account the batch size. So the first dimension is the batch size, but then we are going to put on the second dimension as many as necessary. This would be the length of the sequence of words. But now we're going to add the number of heads as an additional dimension and the depth of each head. So how this is split across the different heads. So if we have the input with the depth of, say, 100, for example, the depth of 16, and we have 4 heads, then we put 4 here, and we leave 4 for each of the heads. So we are just taking the matrix and reshaping it with one additional dimension. And now we're going to switch the order of these two here, just so that when we apply the operation, the scale dot product attention to this whole matrix, it actually works as if it's doing independently each head. Okay? So this is the kind of tricks that you can do, because you can use the tensors in any number of dimensions. So often you don't need to actually do things one by one. You can just put everything in the right tensor and it does it in one go. So this is how we use the layer object. We create this call method that is going to be executed by Keras when it's, or TensorFlow and Keras when it's using the layer. And we, in this case, we receive the values, the keys and the query and the mask. And now we use those linear dense layers to create a new representation of the query, the keys and the values. So this is learned by the attention model here. And then we split this, we change these matrices in order to add a new dimension for the different heads. And now we do the scale dot product attention here with the different heads. And to concatenate everything, basically we need to reshape this in order to throw away the dimension of the head. So we again switch the positions of those dimensions and rescale this so that we have the batch size, the sequence, and now the actual depth of the model. So we bring back to the original representation without splitting into the different heads. Okay, so now this is the multi-head attention that returns this output. So again, this is another dense layer here after the attention, and also the attention weights, which is the result of the scale dot product if we want to visualize them later on. Now there is this part here, this special dense layer that I mentioned here. This is called a pointwise dense layer or a position-wise dense layer because it's going to receive a matrix that has one vector for each word, but has all the words in the sentence. And this dense layer will be the same applied to each word. So it works a bit like if it was a convolution layer, something like that, where you have the same kernel, but in this case the kernel is large because it's all of the values that encode each word, and we're actually going to expand that into higher dimensions. So the architecture, if you imagine this layer looking only at one word, it's going to have its own depth here that can be higher than the original representation of the words. So for example, imagine that we have each word represented as 128 values in the vector. We can have something here like 512, something like that. So the first layer has a ReLU activation and has this larger dimension. So it's going to look at each word, expand it into this higher dimension, and apply this nonlinear transformation. And then we apply to that a linear layer that reverts back to the original depth. So basically looking at a linear combination of this nonlinear transformation and going back to the same original size. But this is looking at each word, and it's the same layer, the same network. The reason why this works then is because if you have a dense layer that has the same dimension as the last dimension of a matrix that you are presenting it, then Keras will do the broadcasting like NumPy and so on, and apply that dense layer to across all the other dimensions. That's why it works with batches, but it also works with additional dimensions. So in this case, the last dimension is the depth, the size of the representation of the word. The one dimension before last is the size of the sentence, and this layer will be applied to the whole sentence exactly as it is. So that's why it's a pointwise or position-wise feed-forward network, because it's going to be applied to each position the same network. Okay, so now we can create the encoder block. The encoder block starts with a multi-head attention, with the depth of the model and the number of heads that we specify. Then we have this pointwise feed-forward network that uses the depth of the model and the depth of that network that is also an argument here. And then we have this layer normalization. Layer normalization is similar to batch normalization. It's analogous, the idea, but instead of normalizing along the batch, it normalizes the values of the layer. So if the layer has some values that are very high, it will rescale everything to have this normal distribution for the layer. And we have these dropout layers here too. So this is to create the object. Basically, to create one block for the encoder, we need a multi-head attention part, a pointwise feed-forward network, 2 layer normalizations, and 2 dropouts. And now, when we call, we do the actual computation here. So we call this with an input value x. We use the multi-head attention on x. In this case, it's a self-attention for the encoder. So x appears on the 3 arguments. There can be a mask in this case, because for the encoder we need to specify which part of the sentence does not exist. And now we get the output of the attention, we apply a dropout, we do layer normalization, then we get the pointwise feed-forward network here, dropout, layer normalization, and that's the encoder block. Now we can do the same thing for the decoder. So in this case, the decoder, if you recall, is a bit more complex. It has this this self-attention, but then this has this multi-head attention receiving the output of the encoder. So basically that's the block that we can implement here. We create this multi-attention, two multi-attention layers. The first one is the self-attention, the second one receives from the encoder, the pointwise feed-forward network at the end, and then this is layer normalization and dropout. So the call function here is where we put this together. We have the self-attention first, then we do dropout, layer normalization, and then we're going to use the second multi-head attention to use attention on the output of the self-attention here, but based on the output of the encoder. So we receive the output of the encoder here, and these will be the keys and the values, and this will modify the output of the first self-attention layer. And then dropout, layer normalization, and feed forward. Now there is one detail here that I forgot to mention, which is this training flag here. This is used for dropout. Remember that dropout works differently when training. When training, it switches off at random neurons, and during inference, when you're predicting values. In that case, it just rescales the output so that on average, like it was during training. So dropout layer, if you're using it automatically in Categorical takes care of that, because when you do train, it does one thing, and when you do predict, it does another. But if you're creating your own, then you need to control that. So in this case, when you're training, you have to put this flag at true, so that dropout layers work as they should when training, by switching off at random some of the neurons. When it's not training, when you're doing a prediction, then this should be false, so that dropout simply rescales and does not turn anything off. Okay, so now we can create the encoder. The encoder is just a stack of layers here for the encoder layers. So we have n of these. These were the ones we saw before, the encoder, and now we have a number of these stacked together before producing the output. So basically, this is what we're creating here. In this array, for each, in this number of layers, we create an encoder layer. Of course, before we get into the encoder layers, we need this embedding layer. So basically, this is a matrix that converts the values, the integer values of the tokens describing the sentence into those vectors representing each word. At the beginning, when we start training, this is random, but then it will adjust so that it improves the performance of the rest of the network, and so the embedding layer will learn the best way to convert integers into vectors in order for this to work. So we have this embedding layer here, then we do the positional encoding. We need this part so that we can encode the different words into different positions, and we need the stack or the list of encoder layers. So when we call this, what happens is that first the vector of integers representing the sentence is passed through the embedding layer. This produces a matrix of vectors for all the sentences. Now we do the encoding, we have this dropout here, and then we apply the masks for training. Let's see. Okay. Okay, the positional encoding, that was the part that was missing here, but we add the positional encoding for these sequences. So basically, we have all of these vectors computed that give different vectors for different positions. and we add that to the encoding, to the embedding of the sentence. Before that, we rescale this. So basically, this is rescaled by the square root of the size of the model, and this is a way of weighting how much weight we are going to give to the embedding and how much weight we're going to give relatively to the positional encoding. So you could fine-tune this a bit, but this is the way it's suggested on the tutorial. But in any case, what we're doing here is we're combining the embedding with the information on the position that slightly changes these vectors. Now we use dropout with the training flag again, and now we're going to go through all of these layers and basically get the output of each encoder block, and then feed that output in the next one, until we reach the end of the encoder blocks, and that is the output of the full encoder. For the decoder, we have something that is similar. We also have an embedding because we need to embed the sentence that was generated so far so that we can predict the next token. We also have positional encoding for that, the same idea. So basically we have the embedding, we add the positional encoding, the dropout, and then go for all the decoder blocks here. Basically, the only difference here is that now we have these blocks that have the information on the weights if we want to represent them. So we have these attention weights if you want to show them, but basically the code is the same. We are looking now through the decoder blocks to these layers, and we are feeding the output of one into the next until we reach the end of the decoder part. Okay, so now the whole transformer, what we need is we need an encoder. They call this tokenizer, but I think it's a bit confusing, but that's how it's in the tutorial. But this is basically the encoder. This is a stack of encoder layers with the embedding and so on. This is the decoder, the part that receives the output of the encoder and predicts the next token. And the final layer is basically a dense layer with as many neurons as the size of the vocabulary on the target language. So if we are translating from Portuguese to English, we need to have a dense layer at the end with as many outputs as there are different words in English in the vocabulary that we are considering. Because this is what will now predict what the next word will be. So when we call this, we call this with input and a target sentence. This is the flag for training, and basically we use the encoder on the input. We get the output of the encoder, and then we use the decoder with the target sentence. This can be the whole sentence when we are training with different masks, or it can be whatever was produced so far that now we want to use to get the next word. So if we want the transformer to produce a sentence, we have to first send in the start token, and then the start token plus the words it produced first, and then the first two words, and so on, until we get the full sentence. So this is the output of the encoder, the output of the decoder, and the final output will be the output of the decoder put into this dense layer, and that would be the output here, where we can now use the softmax for the loss function and so on. Another detail, we can create a custom scheduler here that will change the training rate. So you can do this instead of using a fixed value for learning rate on the optimizer. You can do something like this. This is called with different values on the step argument. This is how many batches occurred, and you can create a formula that will decrease gradually the learning rate through time. So basically this one has a number of warm-up steps where it keeps the learning rate high, and then it will also start reducing with the square root of the step. And basically what we are doing here is we have a learning rate that is the square root of the depth of the model multiplied by the minimum of these two, and so this is something that scales with the depth of the model as the number of steps increase. But this is something that you can write your own if you want. But the idea is that you can create these schedulers, and then when you use an optimizer, you can set that schedule so the optimizer uses that to get the learning rate. Okay, so here are the loss functions that must also include masks, because we don't want to evaluate loss outside where the sentence exists. So this would be the real sentence, the predicted sentence. We can create a mask where the real sentence is 0. So we only care for the places where there is not a 0 on the real sentence. Wherever on places where there is a 0 on the real sentence, this means that the sentence is already over, so there are no words there. We don't want to measure the loss there. And now here we can compute this loss using this loss object here. So basically the loss object is just the categorical cross entropy. That sparse there you can use when you're not using one-hot encoding. So you all use categorical cross entropy to compare if the class is correct on the predicted and the real one. But that one is when we use one-hot encoding for the class. If we use an integer to represent each class, we can use the sparse categorical cross entropy, and that's the situation here. So you can imagine that the words along the sentence are represented as integers. Each integer represents a different word, and we're checking to see if the words match along the sentence. So here we take the average over the whole sentence, but only considering what the actual sentence here. So if the sentence has 10 words, we divide by 10. If it has 15 words, we divide by 15, and so on, after comparing all the words. The accuracy is similar to this, but it measures the percent of words that are equal in the real and the predicted one. Here we can create these matrix objects, the mean objects for the matrix. These keep running averages of these values during the training. So they are useful if you want to follow the kind of thing that Keras prints out when you do fit. Basically, it's a running average of the loss and accuracy values that you get in training and validation. So this is for the loss, this is for the accuracy, and these would be just these metrics for following the values of the loss and accuracy during training. So we create this scheduler for the optimizer. We use as learning rate the scheduler that we created. This is basically the number of layers that we're going to have on the encoder and decoder, the number of heads, and so on, to create the transformer. This would be the size, the maximum position that we are considering for the positional encoding. And these tokenizers, this will be the vocabulary size, would be the total number of words, of different words that we have in each language that we get from the tokenizers that we used before. You can also add checkpoints. I'm going to go a bit faster over on this because this is basically just looking at the documentation, but this allows you to keep a number of checkpoints saved, the model saved, so that if you have to interrupt training, you can restart from where you were. This function creates the different masks. So the padding mask for the encoder and decoder will mask the parts of the input sentence that do not exist. We need to ignore those. The look-ahead mask will be for the target sentence so that we don't see the next word when we are trying to predict what the next word will be. So the transformer works by giving the previous words and it will predict the next one. But if you are using the real sentence, the real translated sentence, you need to hide the next words so that the transformer does not see that during training. Okay, and this would be the training step. This is similar to what we used before. So we have, in this case, we're going to look at the inputs will be everything until the last value. So what we input to the decoder for the translated sentence will be all the words except the last one. This usually does not take words because the total size of the input is larger than most of the sentences. But the target for the output that we want is we start from the second word all the way to the end. So basically we are putting the sentences cropped at the end, but then we want the output to be something that starts on the next word of the sentence. So it's shifted by one. Now we create the masks for these words for each training step. So this is a batch of input sentences. This is a batch of translated sentences here. And now we use the gradient tape to compute the predictions, the loss function, the gradients, and apply with the optimizer. So this is what you've done before with TensorFlow, and we add the loss and the accuracy to these train loss and train accuracy, which are these moving averages that we created here for the metrics, so that we can follow training. Now, the only thing different from what we did before is that usually in our examples we use the greedy execution because it's simpler to work with, where this is just executed as the Python code is run. In this case, we are using this TF function decorator, the one that we use to create the graph, for example, for seeing in TensorBoard, so that when this code is run, what TensorFlow will do is trace all of the computations and create the graph. And then we can execute the graph, which is a lot more optimized for running. The additional argument here is necessary because whenever if you create a function here for TensorFlow to make the graph with this decorator, if the sizes of the tensors that are input into the function are different, TensorFlow will create a new graph. So each graph for different shapes of the tensors. Since these tensors are batches, they can vary in size because when you don't have the right number of examples to fill all the batches, the last batch may have a smaller number of examples. And in that case, if you don't specify the signature of the tensors, it will create a new graph when you get a batch with a different size of examples, and that is inefficient. So this signature tells TensorFlow to expect these shapes to have these tensors to have 2 dimensions, but it doesn't matter what the shape is. So they can be longer or shorter, it doesn't matter, and it will. You are telling TensorFlow that the graph will run all the same, even if the dimensions change. All they need is to have 2 dimensions. It doesn't matter how many elements in each dimension they have. So this way, it will only create one graph, and hopefully everything will work. Okay, so now we train 20 epochs, for example. We can reset the moving averages for training for loss and accuracy, and then we're going to go through the batches, do the training step, print out the loss so far, every 50 batches in this case, and then save the checkpoints for each epoch after the first every 5 epochs, so we keep saving checkpoints. But basically this is the loop through all the epochs and all the batches. This can take a bit, so maybe a few minutes, half an hour, depending on the hardware that you have. So if you want to try this, maybe you can try it in Colab if you don't have a good hardware. And then after the end, we can evaluate the results. So basically, given a sentence, we set a maximum length for the output, and we use the transformer to generate a translation. Basically, we're going to receive a sentence in English, in Portuguese, and output a sentence in English after training this. So first we convert this to a tensor and tokenize it. So basically we receive the sentence as a string, but we use the tokenizer to create the vector of integers for all the words. And now we also do the same thing for an empty string, so that we get the start and end tokens. These are special tokens the tokenizer adds to the sentence, which indicate where the sentence starts and where the sentence ends. So now we are going to iterate until the maximum number of words in the output sentence. We're going to create the appropriate masks and to use our transformer to get the prediction of the next word. So we're going to start with the encoder input to be the sentence that we are given in one language, and the output so far, it's going to start just with the start token there. So we're going to put the Portuguese sentence in the encoder, the start token in the decoder, and the transformer will predict the first word of the English sentence. And now we add that first word to our list of words so far, and we use that again to predict the second word and then the third, and we keep doing this either until we reach the maximum length, or the transformer gives us the end token as the next prediction. The end token means that the sentence is over, and so we break the loop there. So these are some examples. We're going to translate. This is just evaluate the sentence. We discard the different return values there, and then we print the text, the translated text. This is a tensor with the binary, the byte representation of the string. So we are converting it into NumPy and then decoding it to UTF-8 so that we can see the string there. But basically this is just to evaluate or use our transformer and then decode. And this would be an example. Este é problema que temos de resolver e this is a problem we have to solve. Este modelo parece funcionar bem, this model seems to work well. So you see these kind of sentences, the translation is very good. When we start getting into idiomatic expressions, so things that don't quite mean literally what they are there, what is written there, then things start to get a bit weird. So who always wants everything to lose? This is somewhat close, but it doesn't make much sense. Os estás aqui, estás a levar, these are actually taking one over here, so it missed the meaning there. Estou feito ao bife, I'm done by the different tree. So here, I don't even know why the tree comes there, but one interesting thing is that this is not trying to translate word by word. It's not a simple dictionary or something like that. It's looking for patterns in the sentence and trying to look for the words that may fit the pattern. Of course, things that are present in the examples, then it can find those patterns well. If you deviate and go into things that are strange, then it will no longer find the patterns. But it's a lot more sophisticated than just trying to figure out which words go where. Okay, so to sum up this part, there was a lot of detail here that you don't need to know for the test. You can use in the assignment if you want, so create layers, things like that, but it's not mandatory, you don't need to do that. But I wanted to show you something a bit more sophisticated because it shows the power of TensorFlow and Keras, and it shows something that is more realistic, more serious than the kind of toy examples we've been seeing so far. But the important part here to understand is this architecture of the transformer, the attention mechanisms, the way we are modifying the values, the tensors that are passing through, depending on other patterns that tell the network how to give more weight to some parts and less to others, and how the transformer network works to generate these sequences. So it's a feed-forward network, it's not recurrent, but we can use it to generate these sequences of words, because when we present the context, the original sentence, and whatever has been done so far, so the output so far, the transformer predicts the next word. And now we can feed that back in and get another word and another word and so on. So this is an important part here to understand how transformers can replace recurrent networks in a lot of applications, such as translation. We saw how to implement the transformer using lots of more advanced elements and carriers, the data sets that allow you to control reading from the disk in parallel while the model is training, the schedulers and checkpoints to control training and to save the model, creating layers so that you can then add them like you do with the functional carriage, and putting the training into the graph first before running that, because that really makes things a lot more efficient. So if you want, you can optionally read the paper, and also you can follow the carriage tutorial if you want. It's in the documentation.